My name is Petr Brož, and yes, I'm the guy on the right side of the screen. I'm working at the Czech Academy of Sciences, and I'm interested about different aspects of volcanism across the solar system. And today, I would like to show you some results of our experiment in which we performed with my colleagues at low pressure chamber at Open University in United Kingdom. As you can see, there is a bunch of people which helped me during this study, namely Krýza, Lionel Wilson, Susan Conway, and Hauber, Adriano Mazzini, Jan Raack, Patel, Matt Balme, Sylvest, and Mueller. So you can see that this was really quite large project across the different European universities and research facilities. Before I will show you some movies, let's speak a bit about the exploration of Mars in general. So today Mars is one of the best explored planets within the solar system. This is because we have a couple of orbiters which are orbiting the planet and which are gathering the data from orbit. We also have a rover which is moving over the surface, and we also have a lander which is trying to get a deeper insight about the inner structure of Mars. Many of these probes there are providing imageries which we can analyze, and we can try to find, or we can try to reveal what we can see on these images, and to make some stories how Mars was formed, how it evolved, or which different processes shaped the surface. On this image, for example, you can see that we have some impact craters. Over here we have a cluster of secondary impact craters. Over here we have some unit which is standing above the surrounding smooth plains, and in this part of the image you can see that there are some pancake-like features which are associated with the domical or somewhere over here or conical features. And also we have here some flow-like edifices, and these flow-like edifices are actually something which was quite interesting for me because when I start to study them, I realized that there is like something like a sorcerer. You can see some open channel. Sometimes there is just a flow-like unit without the central open channel. So I somehow tend to believe that these features were formed by flowing material which was erupting from below, from subsurface. These features are quite often associated with conical edifices of various sizes. So there was a hypothesis that these features may be actually a result of mud volcanism. However, there is a huge problem. And this problem is associated with the fact that on the surface of Mars we have a really huge amount of kilometer-sized features, which have really different shapes, as you can see on this panel. Some are associated with really by central craters, some others not. Some are grouped, some other not. Some are associated with the flow-like features, some other not, and so on and so on. And there are two main hypotheses what these features are. The first one is saying that these features are sedimentary volcanoes, and the second one is saying that these are real volcanoes, or if you want, igneous volcanoes, or features formed by lavas. As you can imagine, to know which scenario is right has a huge consequences of our understanding of different regions on Mars, because if we will know for sure that these features are sedimentary volcanoes, we would know that there have to be a liquid water or pressurized liquid water underneath, or if these features are on the other hand igneous volcanoes, we would know that there has to be molten rocks in relatively recent past of Mars. So this really has a potential to change the way how we are understanding the evolution of Mars. However, the situation is not very simple. Why? Because there is quite often a situation that, you know, for one field where we are observing these cones, that both hypotheses were actually proposed. So we are not really sure if these features are sedimentary volcanoes or igneous volcanoes. This can be illustrated nicely on the example of a field of pitted cones, which is situated on dichotomy boundary on Mars, you know, close to Isidis Basin. There is a bunch of conical features which have really wide central crater, which is quite often, you know, the floor of the crater is actually lying below the surrounding units, which is quite interesting. They are associated with the flow-like features and so on. I don't want to go into the details, but in principle, there is a paper by Jim Skinner and Kenneth Tanaka from 2007, in which the authors are arguing that these features have to be sedimentary volcanoes. On the other hand, there is a paper by me and Hauber from 2013, in which we are arguing that no, these features have to be formed by phreatomagmatic volcanic activity, and that these features are tuff rings and tuff cones. Then if you will move to other field, which is situated inside Valles Marineris, which is the largest known canyon within the solar system. Again, there are really nicely developed conical features with which are clustered. Sometimes, as you can see over here, they are superposed on some flow-like unit. There is again a paper by Chris Okubo from 2016 in which he's proposing that these are sedimentary volcanoes. On the other hand, there is a paper by me and a bunch of other people in which we are saying no, these are not sedimentary volcanoes, but based on their shapes, spectral data, distribution, we are saying that they have to be volcanic, real volcanoes, namely scoria cones or maybe tuff cones. And finally, there is a field within the Krýza Planitia in which you can easily find around 1,200 different edifices. Some are like conical, some are domical, some are pancake-like, and some are flow-like. And these features were described by Goro Komatsu in 2016 as the results of sedimentary volcanism. And I will surprise you, I hope. This time we really tried hardly to disprove the hypothesis that these are sedimentary volcanoes, but we didn't succeed, and I really believe that Goro Komatsu is right here, and that these features are sedimentary volcanoes. This study was actually quite important for me. Why? Because when I was, starting to believe that these features are indeed sedimentary volcanoes, I start to be again fascinated by the fact how the mud would behave if it extruded on the surface of Mars. So I was trying to find the answer how the mud would behave in the under the low pressure, because Mars is a smaller planet. It has an atmosphere, but the atmosphere is 150 times weaker than the atmosphere of Earth. So I was really wondering how this low pressure would change the way how the mud behave. And when I searched through the literature, I discovered that there's only one paper in which the physics behind the mud behavior under such pressure is described. And this is the paper by Lionel Wilson and Peter Mojinis-Mark from 2014. And in this paper, there are some theoretical considerations and some theoretical predictions how the mud would behave. But even if you will read this paper, you would not really know if the mud would be able to move over the surface of Mars. So simply there was a gap in our knowledge. And now you can ask the question, why this is a problem for us? Why is the problem with, what's the deal? Why we are not just not saying, okay, mud would flow on Mars? And there is actually a huge problem, and the problem is instability of water. Because if you will have a look on this phase diagram, in by this rectangle there is it's bounding, let's say, the conditions which are today on Martian surface, and you can see that the liquid water is mainly not stable. So it means that if you would release a liquid water on the surface of Mars, that it would be freezing, it would be going into the solid, or it would be sublimating, it would go into the vapor. And it's exactly what Bergery and others in 2010 showed in their experiments, in which they took deionized water and they put it inside the low pressure chamber, and they just observed what was going on, and you can see that there was a boiling and there was also some sort of freezing. But still, this doesn't answer the question whether the mud can move on Mars or not. So what we did with my colleague, with Krýza, the guy on the movie, we actually asked Europlanet Society to get access to large Mars vacuum chamber at Open University, which is in the lab of Dr. Patel. This is actually quite large chamber. It's roughly 1 meter to 2 meters in size. Normally, the people who are operating vacuum or low pressure chambers, they are trying to keep their chambers as clean as possible. But in this case, and I think this is the most important part here, Dr. Patel, he doesn't really care how messy or how muddy his chamber will be, as long as we were doing some good science behind it. So he allowed us to make our experiments inside and to see what would happen. So we worked about experimental setup. In principle, what we did is that we took a trail which was infilled by 2 centimeters of sand. We were able to cool down the sand to the temperature minus 30 degrees by inserting the trail with the sand into the freezer. Then when we reached the temperature which we need, we installed the tray inside the vacuum chamber. We also filled our container by really low viscosity mud, which was really water rich, or better to say water dominated. And then we closed the chamber and depressurized, and we just flip it to the container and observed what would happen. So first of all, I will show you 2 movies which are capturing the experiment under the normal pressure. So what you will see here, it's how we are releasing the mud on the surface. The tray is inclined by 5 degrees because we wanted to observe the movement of the mud, so we have to force the mud to actually move. We are splitting 500 milliliters of mud, and the temperature of the sand is minus 20 degrees. And now what would happen? You see that this is actually quite boring, I would say, because this is fulfilling the everyday experience which we have from Earth, but you have to see it to have a reference. So now you know how our mud behaved, and you can imagine what would happen if you will release such mud from below to the surface. You see that you will produce a really broad sheet of mud, which is only a few millimeters in thickness, and that's really something what all of us remember from our childhood. Okay, so let's repeat this experiment, and the only thing which would be changed now is atmospheric pressure. Now the atmospheric pressure inside the chamber is 7 millibars. And what would happen? You see, there is a big difference. The mud is now moving very differently. You can see over here, there is some hard surface on the mud, and the mud is capable to propagate under this hard crust or hard surface. What's going on here? Actually, the mud is freezing. Why? Because water is not stable. However, the mud is able to propagate under the surface of this frozen crust. And this is something which is really cool. Okay, once the experiment was over, we pressurized the chamber, we opened it, and we went to investigate the inner structure of these flow-like features. And as you can see, they look like a biscuit filled by molten chocolate, because what we discovered was that there was icy muddy crust, which was on the surface and on the bottom, but inside there was a body of liquid mud. So it means that the mud was capable to survive there for dozens of minutes, maybe even for first hour. So it looks like that there was some process which was capable to protect the mud from freezing. And also what we observed, there was a huge amount of bubbles which formed and then were captured by ice. Okay, so what does it show to us? Those of you who have a chance to visit some volcanic islands, namely Hawaii or Iceland, and were really lucky because they visited the place where the active lava flow was moving, they probably noticed that the mud in our experiment is moving in quite similar way as some lava flows, namely to those lava flows which are characterized by really low viscosity lavas. They are named as a Pauewe lavas, and these lavas has a tendency to propagate under the protection of the crust, which is solidifying from the magma, or from the lava. The lava is capable to lift up this crust and to move under the protection of the crust. And the same actually happened in our experiments. If I will play again, because what happened here was that there was some formation of the crust. The crust was protecting the mud from the environment, and the mud was able to flow under the protection of this crust. So the process is really quite similar to the movement of Pauewe lava. What we believe, what we know now that is going on. Firstly, why the mud is actually freezing? The reason for that is that once the mud is released to the surface, the water is not stable. There is a boiling which is causing the formation of the vapor. However, there is also a process which is named as evaporate cooling. And actually the process of evaporate cooling, it's capable to remove the latent heat from the mixture, from the mud. And this is causing that the temperature of the mud is decreasing. At certain stage, that's what is shown here on the panel C. At certain stage, there is, the temperature is so low that there will be a formation of a small icy crystals, and they will be slowly merging together until the point where the entire surface of the flow is covered by icy muddy crust. Once this happened, this is a protection. It's actually isolation. So it means that the mud is not in interaction with the atmosphere anymore, and it's able to be stable. There is no more boiling, no more evaporate cooling. However, as the mud is still moving under the protection of this crust, there is some pressure buildup. At certain point, the icy crust is not able to hold the pressure, and there is a breakup. So in this case, when the breakup is the breakup happened, there is a release of mud, and the mud is again exposed to the atmosphere. The boiling and evaporate cooling would start again, and this would cause that that you have flow the formation of the crust again. Big issue which we had was a scaling, because our experiments was performed in meter scale, because the largest flow which we were able to produce were like 1 meters 20. So once we made a really crazy experiment, we actually make a small crater, and we infilled the crater with 1.6 liter of mud, and we observed what would happen. And this is exactly why it was so important that Dr. Patel, he didn't really care, about the mess which we will do inside the chamber, because as you can see, there was a huge boiling. That was really crazy experiment. The mud was flying everywhere, and we were cleaning the chamber for a couple of days. But it was worth it, because what we observed is that even for larger bodies of mud, in this case this is a small, let's say muddy puddle which has a thickness of 4 or 5 centimeters, even in this case we were able to observe a freezing. This is nicely visible on this movie, which is 50 times speed up. You can see that there was some boiling, there was some explosions, but after a while over here there is a freezing from the edges and until the point when the entire surface freeze. Again, once this experiment was over, we pressurized the chamber and we opened it and we had a look inside. We broke apart and there was a liquid mud under this crust. So it's showing again exactly what I just showed to you, that the icy muddy crust is capable to protect the mud from evaporate cooling. Okay, so what we believe now we can explain. First of all, on Earth you have many different mud flows which are different because of the different viscosity of the mud. Some of them are associated with really high viscosities, some are associated with the middle viscosity, and many of them are associated with really low viscosities. Our experiments are really important for this terrestrial analogs. So for those mud volcanoes which are releasing really low viscosity mud, or better to say water dominated mud, which is able to make meters long flows, which are normally really with small thicknesses. However, I will now play wrong button. However, if you will, as you can see on this movie from one desert, where is a flat, where is a flat. These flats are not actually propagating by meter thick flows, but on their edges, because the water has really low viscosity as well as the mud, they are propagating by centimeter thick flows, which would be again strongly affected by the processes which I just showed to you. So it means that even these large flow-like, even those large floods would be really affected by evaporate cooling. It meaning that the way how these features would behave on Mars would be a bit different from their terrestrial counterparts. Now it's really nicely visible that you really have centimeters thick flows. And imagine that if this is occurring on Mars, you have a boiling everywhere, there will be floating icy blocks and so on. Okay, next. But Mars can be also a bit warm. This is a really important point. Many of us has a tendency to think about Mars as a cold planet. is it, because the temperatures is like minus 60, minus 80, 60 degrees of Celsius. However, in some places, in some part of the year, the temperature can be above the zero. So we were quite curious what would happen if we would release the mud on the sand which has a temperature above the freezing point. This is again just to show you some reference. These are screenshots or snapshots from the movie which was showing the experiment performed with the same experimental setup as I already showed to you, but the only difference is that the temperature is plus 20 degrees. This is the temperature of the lab, which was inside the lab. So you see, again, it's quite boring because it's exactly what you expect. But now let's repeat the experiment, but decrease the pressure. And what would happen? I believe this would be quite surprising for you. You can see here that the mud is behaving really differently from those experiments which we just observed. There is a huge amount of boiling. There is a huge amount of small explosions ejecting sandy grains everywhere around, and you see that the flows or the lobes of the flows are actually vibrating during the propagation. So this is just to show you the final morphologies. You see that they are really different from those which you just saw on 2 slides before. And what is important, when we were studying the edges of the active flows, we actually observed that there is a really huge amount of boiling. There is a huge amount of bubbles, and these bubbles are causing the vibration, and these vibrations are actually capable to lift up the mud. So the mud is hovering, or if you want, it's levitating above the surface. And if you would think now that Mars has a lower gravity than Earth, the gravity is 38%, it means that if you are lucky enough and you will see active sedimentary volcano on which is effusing mud over the warm surface, there will be a small droplets of mud actually flying around you, which is something which is totally insane for us as a humans living on Earth. Why this is happening? The reason is that the boiling is producing a huge amount of gases. The gases are leaving the mud mixture from all directions, and they are capable to lift up the mud for a while. So there is a really different transport mechanism from those which we know from Earth. We also observed that during these experiments, the mud was able to eject the sandy particles away. So it means that there was something like a self-burying mechanism. We wanted to know how deep this self-burying mechanism can actually operate. So we took a plastic box, we infilled with I think that it was 35 centimeters of sand, and in the end we discovered that it is self-burying only a few centimeters in depth. In the end, we made a new conceptual model which is trying to explain how the mud would be moving over the hot, or if you want, over the warm surface in the low pressure environment. What is important, we will not have only flow movement, but we would also have levitation, which is a much faster process, allowing to the mud to travel probably further. So this is really quite interesting discovery. Now let's summarize it. What I was trying to show you is that water on Mars is not really stable due to the low pressure and temperature, and this has a huge consequences because the instability of water will significantly affect the way how the mud would propagate. And there are two ways how this how the pressure would affect the way the water is propagating. The one is that if if the mat is moving over the cold surface, there will be freezing because of evaporative cooling, and this would be causing that the mat would be moving the same way as the Pauehoe lava flows. However, if the mat is moving over the warm surface, the mat would be levitating. In both, of course, the nature is not black and white. Sorry, there is nothing like a black and white. There are every time different grades of shades. And for this reason, we believe that there will be, of course, some sort of transition. For example, if you have a mat flow which is moving over the warm surface, firstly there will be a levitation and huge amount of boiling. However, the the evaporative cooling would remove the heat, and in the end there will be still some freezing. So you can have really, in one flow, you can have a transition from levitation ruled flow to Pauehoe like flow. So there would be really interesting flow like sequences on Martian sedimentary flows if there are. And the main message which I would like to say now is that we have a tendency to compare something on the surface of Mars with those features which we know from Earth. However, our work is nicely showing that when you want to compare something on Mars with terrestrial analogs, you should be thinking outside of the box. You should be really trying to understand the physics behind and to be sure that the physical processes operating on both worlds would be the same. If not, most likely this would affect the final morphologies, or if you want, it would affect the final shapes. And if you have something like freezing or levitation, this would mean that sedimentary volcanoes on Mars should look differently than those on Earth. And then it would be really hard to compare something between two planets. So really care should be taken when comparative planetology is done, and we should really try to understand the physics which is behind. Okay, that's it from my side. Thank you very much for your attention. If you would have some questions according to this presentation or some other questions about the volcanism on Mars, please feel free to send me the email to this address, and I'm happy to answer your questions or comments. Thank you one more time and enjoy the course. Bye.